All right, in this video, we just have a transition video from chapters 1 through 4 into chapter 5. So in chapters 1 through 4, we have done differential calculus. We have done recently problems involving antiderivatives. We have done the rectilinear motion problem and the relationship of velocity as the rate of change in the position function and the acceleration as the rate of change in the velocity function. So essentially, differential calculus is about a function f of x that has probably been given to you. Okay, this function could be a position function, right? It could be a velocity graph, right? And in the first part of this course, we've learned about taking derivatives of those functions, okay? And you are able to find those using all the derivative rules that we have done. But you'll recall that the derivative is about the instantaneous rate of change of whatever you're taking the derivative of. So that would be of the function f of x. So we've been talking about the derivative as a rate of change. Okay, and this is related, of course, to the tangent line problem. Okay, and this is what has been occupying our attention for chapters 1 through 4, the tangent line problem. Okay, and the tangent line problem, of course, is that at a certain point C, you want to look at the slope of the tangent line, and that tangent line is a rate of change in the y value over a change in the x. I'll be back in a second. My cat's scratching at the door. Hold on a second. All right, we're back from the annoying cat. We were talking about the tangent line problem and its relation to differential calculus. We know that f prime at c is the limit as x goes to c, f of x minus f of c over x minus c. Okay, and that's the derivative at the point c. And we know that in the context of not just any general function that you've been given, f of x, but maybe the derivative of the position function with respect to t is the rate of change in the position function. And we've got that in terms of this idea called the velocity. Okay, so differential calculus has been all about the tangent line problem and interpreting the derivative as a rate of change. And depending on what function you have been given, that rate of change takes on some very important terminology, and you have some new ideas in there called velocity and acceleration. Okay, so that's the differential calculus problem, the tangent line problem, and the rate of change problem. What we need to do in this new chapter, chapter 5, is to do something similar, that we have a function f of x that would be given to you, right? Or you may be given like a position function. You may be given the velocity, right? You may be given the acceleration. All these will be given. And what we would like to do now is to transition to a new kind of problem called the area problem. So rather than a tangent line problem, we are switching to this thing called the area problem. And of course, similar, that you've been given a function f of x. And what we're going to need to consider is that consider this function on a defined region, x going from maybe a to b, right? And the area problem is going to be to ask this important question: what is the area under this function from here to here, right? What is the exact amount of area there, right? And what we're going to find in that problem, the area problem, is that we'll have to tackle the ways to compute it, what that area problem means, and then we will talk about how the area problem is related to the differential calculus problem. So these ideas, the area and the tangent line problem, turn out to be related in a very interesting way with something called the fundamental theorem of calculus, right? So we will need to, just like we did in the last differential calculus section, spend a little time talking about our new kind of problem called the area problem instead of the tangent line problem. We'll then need to talk about what that new idea means, right? What this area problem means, and the notation for this section is going to be related to kind of the notation that we've done in the antiderivative section, but our notation, instead of this computing a derivative idea, we're going to be computing an integral of the given function, right? And we'll be integrating from x is equal to a to x is equal to b, and we will, this is our notation, and we will find that this is the area of the function f of x from x is equal to a to x is equal to b. Okay, there will be a specific terminology that if you were to integrate from a certain time a to a certain time b, if you were to integrate the velocity function, it turns out that this will give you the distance. I'll put air quotes around this. It depends on the sign of the velocity, but the distance traveled, essentially. Okay, so just like in differential calculus, we'll learn how to learn about the area problem. We'll learn how to compute these integrals, and then we will talk about their interpretation in terms of distance and velocity and acceleration. And in general, just integrating the average rate of change or the instantaneous rate of change. So that's what we will, that's kind of chapter 1 through 4 in the context of chapter 5. And we're going to find again that these chapters are very much intertwined with each other, so they are inseparable from each other, we will soon find. All right, so there is just a very broad overview, and then future videos will explore these ideas in more detail.